Excellent. All connected and ready to go. Okay. So, today is going to be kind of a short day talking to me, which is good for you. In essence, what we want to do is just take a look at making sure that we are understanding basic ideas in the lab work that I've given you. And then, let's see where, answer any questions you might have on the homework, and then turning you loose to do some more lab work. How far did you guys get in the experiments last time? What were you working on?
We got to 8.
You got to 8. What's 8 called? Lensmaker's equation. So you're at the kind of part where you're doing the object image kind of stuff. Zach, did you get your optics equipment all squared away there in Cook?
Yes, we got it. We finished experiment 6.
All right, so you got pretty far. And you're more than welcome to just take that stuff home if you'd like and work on it whenever you want, or bring it to class and work on it, Tuesdays and Thursdays, because that's what we're going to be doing here. Does anybody have any questions so far about what you've learned in those optics experiments? Any difficulties you've run into? Are they seeming pretty straightforward on how to set things up?
I didn't write down any questions, so I can't. But
Have any of you looked at the homework for this week?
doesn't. I didn't think there was anything. I clicked and so everything was available, but I think I might have clicked.
So there is homework.
I think we're on to chapter 26 this week.
Yes. Did anybody do chapter 25?
Yeah.
Did?
That's what we had to open from yesterday.
Okay, right. And then chapter 26, oh, this one, yeah. Chapter 26, I don't know if they have any questions yet. I haven't designed any questions for it, but I will go and check to see if there are any. But this week, what I really want to do is make sure that you can finish the labs that you have. I don't know how many I gave you, but quite a few, I guess, right? But there's, and does the labs that I've given you include the eyeball tank lab? I'd really like to see you get through like number 15 in the telescope. Maybe even 16. So number 17 is a good one too, but it's maybe not quite as valuable. Anyway, by Thursday, I'd really like to see you working on the eyeball tank experiment. So we've got essentially 2 days to try to get through the rest of this packet, and then get onto the eyeball tank. Now, in the book, in this. Wow, there's no, what's going on here? Are you telling me that CNX is down? That's not good. All right, we'll have to open up the book from file, which I know I have somewhere here. Here it is. So, What page is we in this chapter on? It's like somewhere here.
1032.
Yeah, it's 1,000 something. Yeah, that's good. That's about where we're at. Okay, so in this next chapter, we're essentially going to be using the stuff from chapter 25 to look at some specific applications of optics. And the first one that we look at is the eyeball, right here. And the eyeball is a fairly complex piece of optics. And you're going to learn all about it as you do the eyeball lab, but you've got essentially two different lenses. One is called the aqueous humor, and the other one is called the lens. Also includes the cornea, you could think of it as. But the cornea and this aqueous humor act as a lens. And then there's the lens inside of here as well. But there's more focusing that goes on, more things that go on, because the eyeball is filled with water. So you've got multiple things that light goes through, and you know that as light goes through things, it changes speed, and therefore it can change direction. So every time it goes through one of these things, it can changes speed and changes direction. And the whole idea is to get things to focus onto the back of the eye, which is called the retina. Here they show the indices of refraction of the different materials in the eye here, and they show an example of how something would be focused into the eyeball and onto the retina. And notice what kind of an image is this? I'm sorry? It's inverted? It's an inverted image? Is it a real image or is it a virtual image?
Real.
It's a real image, right? So the real image is actually projected onto your retina. So if you could actually look at your retina, you would actually see images of the things that your eyeball is seeing projected onto your retina. And the way that it gets to your brain is that your retina is connected to this nerve down here, and there's a hole in your retina right here. You guys ever heard what that's called before? That's called your blind spot. You ever looked for the blind spot in the eye test where they have you look for things as you go sideways and then all of a sudden something disappears? That's where that is. That's when your eye is focusing something onto the actual nerve. What's your question?
Awesome.
Oh yeah, you're looking for your blind spot. Yeah.
Yes.
So anyway, so yeah, that's actually where your blind spot is right where that nerve comes in and connects to your retina. So it's quite an interesting piece of optics here, but it's also not a strictly static optical system. This system is very dynamic. It can change. For example, you'll notice there are muscles up here and down here, these fibers and these muscles. Those things can stretch this lens or squish it. So they can actually change the curvature of the lens, therefore changing the focus of the lens, right? And that happens when you're trying to focus on something that's far away relative to something that's closer up. Your eyes do that automatically as you're trying to focus on things. You also have this thing in front of the eyeball called the iris, which opens and closes, essentially makes a smaller hole here for light to come through, or a bigger hole for light to come through. What is that going to do for your optics? Remember what happens if you have light hitting the very curvy part of the lens? What happens there? Does all the light focus at a single point? No. Remember the aberrations from a spherical aberration? If the light goes out on towards the curvy edges of the lens, it no longer hits the lens at a 90-degree angle or close to a 90-degree angle. The angle between the light and the lens becomes off, and so it actually focuses differently. And you get many focuses and you get blurred images. You ever have an experience where your eyes are very, very blurry? When are your eyes most blurry on a daily basis? What time of day? Okay, at the night when you're sleepy is one time. What's another time? A really important time that is obvious to everybody. When you first wake up, don't you always have to kind of blink things away and kind of like adjust your vision, especially if somebody flips on the lights in your room? Well, the problem is with that is when your eyes are closed, your irises close down, they relax, and they make these very, very small holes. No, sorry, they relax and make very, very big holes. Small holes are contracted muscles, big holes are relaxed muscles. So they make very, very big holes, right? Relaxed holes. And that opens up the lens so that the lens is open to any light coming in it. Since your eyes are closed, it doesn't matter. Then you wake up and you open up your eyes, and all of a sudden all this light comes in your eyes, and it's all focusing in different places. So you get a very blurry image of things around you until your irises start to close so that only light comes through hitting this flat part of the lens in the middle. The flattest part of the lens. As you get further out, it just gets more and more curvy, right? So that is the purpose of the retina, or sorry, the iris, is to adjust the amount of light that's allowed in. At nighttime, you definitely want to have those open so that you can see better, right? So at nighttime, your iris is open way up, you relax way down, and the muscles relax, and they open way up, and you get lots of light in. But at night, can you see very good details? No. Your vision is very blurry at night. And rightly so, because it's dark, and your eyes are opened up, right? So, here they show some ray tracing with objects in the eye and how that works. Now this is oversimplified. They're showing this ray tracing as a single focus. It's focusing right as it hits the eye. That's not true. First it focuses here, then it goes here, and it focuses here, and then it focuses in the eye. It focuses as it goes through each element of the eye. So it focuses a different amount. So this is an oversimplification. But it's a basic, I mean, you can simplify to that if you make some assumptions. But the equations that you use can be very much the same. If you assume that all the focusing is at a single point. So in this case, they're assuming that all the focusing happens as soon as it enters the eye. And it works well enough to make to get some calculations out, and they do that here with the thin lens equation, or this is actually the lens maker's equation because it's power instead of 1 over full focus. But how do you correct vision, and why do you correct vision? Well, it turns out that there are pretty much 2 types of eye problems when it comes to bad vision. There's 2 major types of eye problems. These are the 2 most common. The most common is when your eye is too long. So this is the case when your eye is too long. And this is the most common thing, one of the most common genetic defects in the human race, actually. There's very few defects that are more common than this. Where the eyes are just a little bit too long, and so instead of focusing on the retina, they focus in front of the retina. And this is okay as long as you're looking at things that are fairly close to you. Within, for most people, within a meter. If you're looking at something that's close to a meter, your eyes can accommodate for that by adjusting the lens so that it focuses onto your retina. For me, it's a little bit less than a meter. I have pretty bad eyes, and the furthest thing that I can focus on is about 20 centimeters away. It's about right here. It's about as close as it gets for me. Most people with myopia have a little bit further, a little bit less of a problem than I do, but that is essentially what my problem is. So how are we going to fix this? What do we need to do to get this to focus on the back of the eye? We do need to change the focusing here, but how do we need to change it? Do we need to focus it more tightly or less tightly? In other words, we don't want it to focus so much after the lens. We want it to focus. So what kind of lens should we put out here to make it focus less? A negative lens, right? A concave lens. And that's exactly what I've got on my glasses. And you can tell that I've got concave lenses. How can you tell? My face is not enlarged behind the lenses. My face is actually shrunken behind my lenses, right? And that's what you normally see with people who have glasses. With most people who have glasses have a little shift of their face so that their face looks smaller behind the lenses than in front of it than it is. So for those who have very, very eyes that are too short, the focus is behind their retina. It focuses after it hits the retina, or it would focus after it hits the retina if it actually could continue focusing. So for those ones, you need to put a focusing lens that focuses it sooner, focuses it tighter, so that it hits the. And this is called hyperopia. So this is what we call nearsightedness, myopia. People who can see things within a meter distance-ish, somewhere in there. And then there's hyperopia, and those people can actually accommodate for things that are very far away, but they can't do so well for things that are close. It's too much change for their eye to handle. Now there is another way of thinking about this. With myopia, the lens would be too strong and focus it too early, or with hyperopia, the lens is too weak or doesn't focus enough, and it causes hyperopia. But it's I believe it's my understanding that the actual length of the eye is the more common thing that happens, not the actual lens formation, but it's actually the eyeball. The eyeball length is kind of goofy. I guess you could think of it either way, though. It doesn't really matter which way you think about it. But anyway, here they show the negative lens, which focuses this light further back in the eye so that it focuses on the retina instead of up here where it was focusing before. And they actually do the math for that lens. They want to defocus the light by a certain amount, and they calculate the power of the lens using the lens maker's formula. And then the same thing for the far-sighted person, right? Now, in both of these situations, there's kind of an interesting thing that happens. This lens does two things, actually. It both focuses the light for this nearsighted person. It focuses the light further back onto the retina, but you can also think of it as making an image that is actually on the same side of the lens. So it's actually is it virtual or real if it's on the same side as the object of the lens? It's actually a virtual image, right? Because real images are on the opposite side of the lens from the object. So this lens, you could also think of it as making a virtual image that's really close to the eyes. That's at about 1 meter or less out in front of your face so that you can focus on it. Either way, it doesn't matter how you think about it. Either way, your eye is able to create an image on your retina. But the same thing goes for the person who is farsighted. For the person who is farsighted, it takes a close-in object and puts an image that's further out that they can focus on, because their eyes focus on things that are further away, right? So you can think of it either way, that it either combines with these lenses to focus that image on there, or it creates a new image for your eye to focus on. Either way is truly correct, and either way results in the same thing. Now there's something else that happens with eyes, and this has to do with the lens and the cornea, and that has to do with what we call we call this what do we call this? A stigma. Astigmatism, right? A stigma. So a stigma is how spherical is the lens on your eye. That's what a stigma it means. If you have an astigmatism, it means that your eye is not very spherical. In other words, it doesn't curve the same amount going every direction from the center of your eye. So if you go to the center of your eye and you go up, it curves a certain amount, but if you went sideways, it curves a different amount in a different way. And if you have an astigmatism, that's what happens. And really how that's caused is there's something going on in your eye that is squishing the lens in one dimension or another. So it's kind of bending it, it's like wrapping it around a pole or something. So that it kind of has some cylindrical quality to it in one dimension. And the way that you test for that is you look at a chart like this. With my glasses on, each one of these sets of triple lines is pretty much equally focused. But if I take off my glasses and I cover my right eye and I try to bring it into focus, the up and down lines are out of focus and these ones are in focus. That means that my eye has an astigmatism in this direction, in the direction that it's in focus. And the way that it's out of focus, my lens has been bent that way. So my astigmatism is here. This is my astigmatism is actually a little bit between here and here. Mine's a little bit off kilter there. And then if I cover my other eye doesn't have as strong an astigmatism, but it's still there. My other eye has an astigmatism kind of in this direction, maybe here. Kind of hard to tell with this eye. And so to fix that, they have to put a serious bend in the lens of my glasses. So if you notice, if you look closely here, I'll put it in front of the camera so you can see it. So if you look at my glasses from the edge, you'll notice that this side, the lens is fairly even. But on this side, you can see that you can kind of see, that it's got this fat side to it. This side doesn't have a very fat side on it. It's kind of flat. This side, it sticks out quite a bit, right? And that's actually pretty good. My other glasses were worse because I used to wear glasses that were acrylic instead of polycarbonate. And then I wore glasses before that. Polycarbonate has a much higher index of refraction, so it doesn't have to be curved as much to have the same effect. But glass and plastic have a lower index of refraction, so they have to be curved much more. This is the reason polycarbonate is being used in glasses so much these days. Not only is it strong and light, but it has a high index of refraction. So it makes for great glasses as far as people that have bad eyes like me. I don't have to wear these big old thick lenses on my glasses. They're heavy and they just look goofy and everything else. So. Okay, so, here we go. Laser, you've heard of LASIK corrective surgery, right? So in LASIK surgery, I'm trying to remember which part they actually cut. Yeah, it's cornea. So in laser surgery, they come into the eyeball and they reshape the cornea, which is which part of the eye? Right, where is the eye? Right here we go. They reshape the cornea right here. Well, that's not a very thick part of the eye. It's a very thin part of the eye. It actually has some effect on what's going on, but not as much as other things. So if you need a serious correction, they're actually going to make this really thin. So it's for most people, what they're going to do is they're going to make it really thin here in the middle, and leave thickness on the outside. So they're making a lens out of your cornea, a better lens out of your cornea. Well, there's problems with that. Why are there problems with that? This eye gets stretched all the time, pulled on, stretched on as it's focusing. Not only the lens here, but this stuff out here gets pulled on and stretched on, and it gets worn out as you close your eyes, open your eyes, as your irises move in and out, everything else. And this stuff in here is aqueous, it's water, it's like liquid. And this liquid is constantly being changed, the pressure in there gets changed regularly. It changes to account for the pressure in the outside air. So have you ever had your eyes hurt when there's weather? That happens because the weather changes very quickly and your eyes haven't had time to adjust. So your eyes feel a little bit of pressure in your eyes. Sometimes you get a headache from that. Your eyes have water coming in and out of them all the time to adjust for the pressure in the air outside because they're squishy things. If there's more pressure outside, you need to have more pressure in the eyes to prevent them from collapsing. Okay? Because of that, this cornea gets a lot of stress in it. And if you thin that thing out, which is the only thing you can do for corrective surgery, the only thing you can do is thin it out. You can't add to it. You can only they just shave off layers of it essentially. If you thin that out, as you get older, you're going to have a high risk of eye problems. Okay, so this is the problem with laser surgery. Now, why do they do it? So why do they allow it? Well, because it's easy and it's non-invasive. You don't have to cut into the eye. You don't have to actually do anything to change what the eye, how the eye functions. All you have to do is shave some stuff off the top. And it doesn't require any skill because it's done by a computer. The actual surgeon doesn't do the actual surgery. He just lines it up. He's not actually a surgeon. If you before LASIK, when you did eye surgery, you actually had to be a certified surgeon. So you had to go to school to be surgeon first, and then you had to go to be an eye surgeon. So you had to be in school for 15 to 20 years when you were, by the time it was all said and done. 15 to 20 years to be an eye surgeon. Now, all you need to do is be certified to do LASIK surgery. You don't have to be a surgeon. You don't even have to be a medical doctor. All you have to do is be an ophthalmologist. Well, I think you can even do it as an optometrist. You might have to be an ophthalmologist, but anyway. So you might have to be a medical doctor. But anyway, the point is it requires so much less skill and so much less education and prep time. So it brought laser surgery to the masses. It's very, very cheap compared to real eye surgery because it doesn't require an expensive doctor to do it and because it requires just a computer to do it. And so they made it available. It's not a good idea, honestly. And the people that developed it actually said we shouldn't be using it for eye surgery. They didn't develop it for eye surgery to begin with. It was developed for sinus surgery. I actually know one of the doctors who developed it.
For what?
Sinus surgery. So sinuses have very similar tissues to the eye, very delicate tissues, and it's very difficult to cut them without damaging them. And so, so anyway, the point is that LASIK surgery is something that you and they do tell you this when you go in for LASIK surgery. They do tell you if your eyes are beyond a certain level of bad eyes, they'll tell you how much risk there is. But they kind of play it down, unfortunately. They're not required to tell you everything. They're not required to tell you that, for example, they never really did any long-term testing with this procedure. LASIK surgery has been around for 20 years now. Before they approved it, they did testing on it for 10 years. So, but the projections from the experts say that 30 to 40 years after surgery, eyes will start to fail. Just about everybody who has LASIK surgery will start to have weakened corneas, and their eyes will start to fail. Their surgery will be for naught, and their eyes will revert back to how bad they were and then get even worse. And I don't say this to scare people. I say this to inform people because this happens in science all the time, where the physics is ignored, even the biology is ignored for the facts, for the sake of money and profit, which is all that it's, and also convenience. People don't want to wear glasses. They want to look great without glasses or whatever. And so they decide to do this. For the same reason we have contacts. Contacts are not generally approved of by ophthalmologists either. Optometrists give them out all the time to people, but contacts are really bad for the eyes. They're the leading cause of eye infections in the world, and eye infections are the leading cause of eye problems, like blindness kind of things. So people don't talk much about those things, but because of money, and convenience, because it's so convenient and it makes so much money for the medical industry. And the medical industry is an industry of money making. Make no mistake about it. They're not in the healing industry. That's not what they're here for. They're here to make money. They're making money off of science, and so it's unfortunate but true. And it doesn't mean that there aren't good doctors out there who want to help people. That's not what I'm talking about. I'm talking about the industry. I'm not talking about the people. I'm talking about the businesses. The businesses in the health industry are not about. They're mostly about money. It's about making money, and they make a lot of it through this. So that's LASIK surgery for you. The previous surgery, I should tell you what they used to do, and they still do. If you really want to get your eyes fixed and not have to worry about them ever getting worse again, you go to radial keratotomy, which is, dang it, this book is really obnoxious. In radial keratotomy, what they do, and I can't remember if they do it on the cornea or the lens. I think they actually do it on the lens. What they do is they open up the eye and they make some incisions in the lens. And then as the lens heals itself, which it will do, it heals in a different shape because of where you put the cuts. And they've been doing this for 60 or 70 years or something like this. They have a lot of data on this, and they know exactly. So that for anybody's eye, they look at your eye and they look back in the records and they say this is what is exactly what is going to happen if we put in these particular cuts in this particular shape of lens. And so they do that, and then the lens heals, and when it heals into the shape that will focus the light the best to your retina. The upside to that is that it heals actually stronger than it was before because of some small scar tissue in there. It's not much, but there's some scar tissue that actually reinforces the lens. The two downsides to this surgery are there's one more upside I'll tell you about in a second. But the two downsides are, one is it takes longer to heal. Instead of hours, it takes days to heal. So you have to wear eye patches for a week or less. And then the other downside is that sometimes people experience some refraction off of the scar tissue at night with bright lights on a dark background. So sometimes they get a kind of a sparkly effect from lights at night. Not always, but sometimes. Depends on the person and the extent of their surgery. The other upside, besides having an even stronger eye than you started with, is really quite simple. It can be fixed if it goes wrong. Whereas if LASIK surgery goes wrong, and it does sometimes, it cannot be fixed. There is nothing to be done. Because you can't just go in and take more stuff off the eye. Right? So I say this to my students, again, not to scare them, but to inform them. I would not recommend, as an expert in physics, LASIK surgery. And this is not just from my expertise. This is from the expertise of one of the people who developed LASIK surgery. Because in 30 or 40 years, you don't really know what the results are going to be. We don't know if that shaving of the cornea off is going to cause a collapse like is thought it would. But they do warn you. I mean, it's in the paperwork that this is a risky surgery that could result in worse eyes than you started with, but they don't point it out very much. Yeah?
Was this the guy that was in Brazil?
Yep.
So you were going to have your lens?
Yeah, so he does radial keratotomy. Yep. So he was one of the leading radial keratotomists in the world yet today, still today. And radial keratotomists are a dying breed because nobody wants to go through 15 to 20 years of schooling to become a surgeon anymore. It's just too long. So many surgeries are becoming automated all over the body. It's, you just kind of set up the instrument and press go. And it's easier and cheaper to do that. And in fairness, it's actually safer in many ways. In many surgeries, it's safer to have a computer do the work than a human hand do the work. Not always, but in many ways. And so it's that is definitely becoming a more common thing. I couldn't say how common, but it's definitely becoming more common. Computers are playing more of a role in surgeries than they ever have. Good thing in some cases, maybe not so good in others. You'd have to talk to a surgeon about that, I think. But science, the physics, infiltrates itself into just about every science. Of all the medical sciences, this is the only one that I really ever considered besides nuclear medicine, because it is so steeped in physics, because physics is such a big part of it. And also because I really just can't handle blood and guts. And the eye just doesn't have much of that. The eye has very tiny little blood vessels in it, and it just doesn't bleed very much. So anyway. Okay, so the last things that they talk about in here are how the eye sees color. And the eye sees color in different ranges and different ways. And the eye sees darkness and lightness, in other words, intensity, in different ways as well. The eyes tend to see changes in intensity rather than actual intensities. You can see there's a spike here whenever there's a change in intensity. So if it's a smooth change in intensity, your eye doesn't seem to sense it so well. And you can really tell that when you're out early in the morning and it starts to get light. All of a sudden you're like, it's light outside. I didn't even notice that happening, because your eye doesn't sense that gradual change. It senses like a flashing light in the corner of your eye, no matter how dim the light is. If it's brighter than the background at all, it notices it, because our eyes are sensitive to change in intensity much more, to a big change in intensity, much more than gradual change in intensity. Our eyes also see, essentially our eyes are, excuse me, our eyes are sensitive to three kind of regions of light. One of these regions is kind of in the reddish region, one of them's kind of in the green, right in the middle of the spectrum, and one of them's on the high end in the blue kind of spectrum. And those things correspond with some physiological and geometrical things in the cones of our eyes, where the wavelength of the light actually resonates kind of with the cone, you could think of it as. You could also think of it in a more modern context, which is a newer model of how this works when it comes to the energy of the light, how it's associated with the wavelength of the light. And that's more of a modern physics thing, where we're talking about particles of light energy that we call photons. But essentially what it comes down to is that we see three colors, roughly. It's not exactly how it works, but we are very sensitive to three fairly specific colors of light: red, green, and blue. And any mixture of those gives us a quote-unquote sensitivity to the visible spectrum in general, so that we can mix those and see different colors, quote-unquote see different colors. But really we're just detecting different waves, different wavelengths, because of a type of resonance within the cones of our eyes, which is actually why they're shaped like cones, because a cone gives you kind of different geometries where different wavelengths will fit in. You could think of it that way. It's not exactly a perfect way to think of it, but it's not a bad way to think of it either. And I'm not being mysterious on purpose. I'm being mysterious because it is mysterious. The way that we see color is still very much a theory. We don't really have a lot of confirmation of that theory through experiment. We have some, but not a lot. It's difficult to do experiments with, but we're learning a lot more about it every day. Here we use compound optics to make a microscope. So you have two lenses, one that's called the objective lens and one that's called the eyepiece. And with a microscope, generally your objective lens has a very, very small focal length, and your eyepiece has a longer focal length. And you create an image somewhere in between them, or somewhere up behind them, or somewhere, so that your eye can focus on that image, that image that you make. So, for example, this first objective lens makes an image between the eyepiece and the objective lens, but the eyepiece actually uses that real image as its object. So it has a real image as its object, which is a virtual object, you can think of it as. And then it creates an image way out here, which is a virtual image that is huge. Look at the size of this virtual image. Well, and it's not very far away from the eye, so your eye can focus on it really nicely so you can see details. All right? So this is a little bit tricky. You have a real object making a real image, and then the second lens uses that real image as a virtual object to make a virtual image. Strange, but it's the way it works. When it comes to microscopes and telescopes, we often talk about magnification instead of focal length or anything else. And with multiple lenses, you have to talk about the magnification of the objective and the magnification of the eyepiece together. When you multiply them, that gives you the overall magnification of the instrument, of the microscope in this case. So they use that as the thin lens equation and that magnification equation to calculate the the overall magnification of a microscope, and it's not that difficult. With a telescope, it's a little bit different. Oh, here they also talk about the aperture and so this is called the numerical aperture, right? Numerical aperture. And then they also talk about the F number right here, F stop or F number. And what these have to do with is how much light is being allowed in. So if you use the numerical aperture, which is, they use the hashtag sign for that. So if you calculate the numerical aperture, which is essentially the angle from the point of focus, so this is actually that you could think of the power as so power is 1 over the focal length, right? So it's another distance from, well, it's 1 over a distance. But anyway, sorry, my voice is totally dying on me. If you use this, if you have this distance here, you get this angle between the edges of the lens to that point, which is usually the focal point. But this angle here tells you how much light gets focused geometrically. Any light that falls outside of the lens won't get captured by the lens and then won't be in this cone. So this angle in here becomes quite important. And you could also use these distances instead of angles, because it's all just trigonometry. But in this thing, they use the angle, and they use the angle divided by 2 to be this angle alpha here, this theta divided by 2 to be alpha. And then n times sine of alpha, where n is the refractive index of the material that you're using, gives you this number we call the numerical aperture, which is a measure of how much light is allowed in. And then the numerical aperture is used, let's see, I think that they're using this, yeah. Well, anyway, so this is a weird thing here. This term, it's got an F slash and the hashtag thing. That's called the F number or the F stop. Either way, you can think of it as. In photography, it's usually called the F stop. In microscopy, it's usually called the F number. But this is the focal length divided by the diameter of the lens, which is about equal to 1 over 2 times the numerical aperture in most situations. So both of these numbers, the numerical aperture and the f-stop, give us an idea of how much light is coming through. With the numerical aperture, bigger the number, the more light coming through. With f-stop, smaller the number, because it's 1 over the numerical aperture, then with the f-stop, the number, smaller the number, the more light it comes through. So with zoom lenses, you usually have, where's our thing here? I lost my picture. Here we go. With a zoom lens, what you usually have is a very, very long throw, or a very, very long focal length. And so this gets longer and longer and longer, and what happens to this angle? Smaller and smaller and smaller and smaller. And so this angle gets smaller and smaller and smaller, and as the angle gets smaller, the sine of the angle also gets smaller, right? And so as your zoom lens gets longer and longer and longer, your numerical aperture goes way down, your f-stop goes way up. So what do they do with zoom lenses? What do you see with a zoom lens? They make so for a short zoom lens like this, you can even see it where the lens at the end here is actually quite a bit bigger than this other end. This lens here is like 10 times bigger than the aperture on the back side. But if you have a really big one, you can really tell. Look how big that gets. This is like a 2-foot long zoom lens, maybe even longer. It gets really big. If you really want to get big, you got this one right here, right? Humongous. And they do that so that that angle can be bigger because the lens at the end is bigger, so they can gather more light, right? But just like with the eyeball, with that big lens out there, what happens to your image? It gets a little blurred. So they actually have to compensate. They have to put more lenses in, the zoom lens, to compensate for that, to fix that blurring. So sometimes these things they'll have 10, 15 lenses in them that are just compensating for all the blurring effects as it goes through. If you've ever lifted one of these, you know that's the case. Pretty much anywhere you see a little break in the lens, like right here there's a lens, right here there's a lens, right in here there's probably 2 or 3 lenses, and then back here there's going to be some lenses. Pretty much anywhere you see a break in that body is where there's a new lens in there. And that's why they get quite expensive, $12,000 and everything else. You've got all these really expensive lenses because of the multiple optics that have been put in there and balanced out just right to get rid of that effect of spherical aberration. Lost our book here. There we go. And here they show that if you have just a straight tube here, the only light that's going to actually reach the end has to actually get to the end. And this is actually not what they're talking about here, but that's still what's going on. So, but what if we put a little reflector on the inside of here? Well, that's what we talked about when we talked about the fiber optic, right? So we do that. If we have just the right angle coming in here, then we get total internal reflection. Put a cladding here that makes it even more reflecting, and then you can have total internal reflection inside of a piece of material. So you can actually calculate how big the end of a piece of fiber optic should be for a particular wavelength in order for all the light that comes in, that can come in, to be totally internally reflected. They call it the full acceptance angle. Do they calculate it here? No, they just talk about it. But for certain colors of light, they actually there is an actual ideal width here. And that ideal width has to do with these ideas we've just been talking about along with total internal reflection. They don't actually talk about it, but they don't actually calculate it, but they do talk about it. So here they show a couple of different ways that you can make a microscope do what it does. This is your This is kind of your standard microscope here, where you have your specimen in the middle, and then you have, well, that's not the standard one. What am I looking for the standard one? Oh yeah, that is standard. So this one down here is for this is where the light lights up the specimen. And then you have your objective lens here, and then way up at the top you'll have an eyepiece lens. And that's one way that you can get light to your eye, one setup. Another one is to have a mirror under it, where light comes from outside this microscope somewhere and hits a mirror, goes through the specimen through the objective lens. Some of them have more of a concentrated light coming through this condenser lens on the bottom. And then some of them actually use a specific light that comes from the side, so they actually have a light source over here that comes in from the side and shines light on the specimen. And this last light here is actually it's essentially a two-way mirror that allows you to see through it as you light it up from the side, usually using a laser. And then they talk about electron microscopes here, which is not exactly the best time to talk about electron microscopes. Electron microscopes do not use visible light at all, and they have nothing to do with your eye seeing anything. And so I'm going to not talk about them. That's something to be talked about when we talk about quantum mechanics. Now, how is a telescope different from a microscope? Well, obviously a telescope is usually used for looking at things far away, but that's not always true. The best way to talk about the difference between a microscope and a telescope is that a microscope has an objective lens with a very, very short wavelength, a very, very short focal length, so that the object that you're looking at is put very, very close to the objective lens. Right? And you're trying to make a big image of it that you can focus on and see details on. With the telescope, you're trying to look at something that is a fair distance away, well away from the objective lens compared to its focal length. And in fact, you're also not trying to make an image that's bigger than the object. With a microscope, you definitely want your image to be bigger than the object. That's not true with a telescope. With a telescope, you're trying to make the image bigger angularly, but not bigger necessarily linearly. What does that mean? Well, for this, and this is a bad drawing, let's imagine that this, well, the reason that this is a bad drawing is because we don't have room here. But imagine we're looking at a tree that's way off the page, way over somewhere. And the light that's coming in are these blue rays to a telescope. The objective lens in the telescope will make an image of that object inside the telescope somewhere, very similar to what the microscope does. And then the eyepiece will make another virtual image of this, but it's not going to necessarily be huge like this. Well, it will be big, much bigger than this object here, the virtual object here. But this final image is not necessarily huge compared to the original tree. I mean, the tree is much bigger than this. The better example is if you're looking at the moon with your telescope. The image that your telescope makes is not bigger than the actual moon. That'd be ridiculous. The moon is humongous. It's so big. You're not going to make an image that big and be able to have any advantage at looking at it. But what you can do is you can bring the image closer to your eye than the original object. Is this real?
May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area.
Okay.
The tornado warning has been issued
Because of winter storm watch, there's no tornado warning here.
May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area.
I guess we have to go and hide in the bathroom.
Go hold hands in the back.
Should we bring the computer and teach more physics in there? Let's go, you.
May I have your attention, please? May I have your attention, please?
Minecraft is
The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time. May I have your attention, please? May I have your attention, please? The tornado warning has been issued for this area. The tornado warning has been issued for this area. Please take all appropriate safety actions at this time.
All clear. There's E all clear.
So ridiculous and stupid. All right. Sorry for that, Zach. Hopefully,
That's fine.
did you have to have a drill there too?
No.
Oh, goodness.
That's funny.
That was just dumb. Let's go stand in the bathroom and stare at each other. Okay. I've actually attended multiple colleges and taught at multiple colleges, but this is the only college I've ever had drills at. Ever. It makes no sense to me. And I've lived in places and been in places where they have earthquakes and all kinds of things, all kinds of reasons to have, emergencies, but they're just like, well, we assume you're adults and you can figure it out. Goodness. Oh well. All right, so let's move on, I guess. So we were at the telescope, and the idea of the telescope, the way it's different from the microscope, is instead of creating a very large image that is much larger than your original object, you're going to create a smaller image, but it's going to be much closer. So you'll be able to focus on it once again. So the result is the same, that you get an image that you can actually, that you can see details on, because it is at a good distance from your eye, so you can actually see it. The other thing that telescopes and microscopes do that may not be immediately obvious is what we call angular magnification. They create this image that is so close to us, and the angle between the top and the bottom of the image is much bigger than the angle between the top and the bottom of the object. And what that does is it essentially spreads out the details and gives our eyes an opportunity to distinguish different parts of the object, because that angular magnification is quite important. And with the telescope, that's how we actually calculate the magnification of the telescope, is by its angular magnification. So if you have an original angle of the light coming in between two different light rays coming in, and then this final angle to the image here, you get, so this would be your original theta and this is your theta prime. Your theta prime over theta, which is the magnified angle over the original angle, the object angle, is equal to your magnification. Now this is actually not equal to the distance to object over distance to image anymore. This is actually now equal to negative the focal length of the objective over the focal length of the eyepiece. And that's because of the multiple lenses. With multiple lenses, these equations get a little bit more complex, and you have to realize that from the get-go. Here we have a telescope that has 3 lenses in it. It's essentially you can think of it as a right side up telescope, where you have an objective lens, an eyepiece, and then you have a lens in the middle called the erecting lens, which actually flips the image over to make sure that what you're seeing is right side up. Now this is very useful in things like hunting, right? When you're hunting, you don't necessarily want to see an upside down deer in your sights. And so they use an erecting lens inside of the telescope on your rifle. And you can do the same thing with mirrors. This is the setup for what we call a Newtonian telescope, which is like the ones I have in this room. It's like the Hubble telescope, where you have an eyepiece and then you have an objective mirror, and then you just have a flat mirror that turns the light sideways so that you're not in the way of the light coming in. And the advantage of this, of course, is that the light doesn't have to go through many things. Right? It only has to go through the eyepiece. It just bounces off everything else. And so you get rid of the aberrations that you might see when light has to go through something. Quite useful. And this is very useful if you're trying to look at, instead of visible light, you're trying to look at light that doesn't go through a lens very well. For example, radio waves, infrared, microwaves don't go through glass all that well sometimes. And they don't focus through glass very well. And so, in other words, they don't turn as they go through glass. That they don't go through glass is not true. They do go through glass, they just don't turn very much as they go through glass. So they're not focused by glass very much. But they are focused by bouncing off of metal. And so if you use a big radar dish and bounce it off the metal instead of putting it through glass, you get a much better telescope for longer wavelengths. For shorter wavelengths, it turns out that you need to do something entirely different. And so what they use is they actually use, it's almost like a total internal reflection kind of idea, where they turn the lens, they make the lens in a cylindrical format, and then they shape it, they make it a tighter and tighter cylinder, kind of like a cone. And it guides X-rays and high energy rays like ultraviolet light, high energy ultraviolet light, guides them into a tighter cone of focus, and then you can focus light that way. There's the Chandra telescope uses that up in space now. So, yes, sir.
That one telescope you showed us with the gold plate.
Yeah, the James Webb.
Yeah. So it has it looks somewhat like a satellite or a bounce back. How does it?
Yeah, that one works just like this. Just like this. Except instead of having a single mirror, it has 16 of them, and they all can adjust to focus, right? And then it has, instead of having one thing like this and an eyepiece, it just has a camera out here that collects all of the light and processes it, right? Since nobody actually looks into that, it just has a camera. A camera is a very simple way of putting it. It's a detector. It's a very high quality, a very high technology detector. Yes.
So I heard about these cheesy on casino TV, new wave cookers that supposedly use infrared,
Yeah, you can actually use something like this to cook a meal.
and they would have like a glass dome over it, and it's because
Yeah. In fact, those were pioneered actually by one of my professors. He actually invented the first one and had got a patent on it. But then he released the patent to the general world, so that because what he didn't actually want to develop it. He just didn't want anybody else to have the right to develop it. So what he did is he essentially published it and patented it, and gained the rights to it. And then he said anybody can use this as long as they're not making money. And so they started using these in. And they're called solar cookers in general, but and they all look very similar. They all, so this is the most like the one that he invented, is most like this. There you go. Where you have some kind of a parabolic or spherical mirror, and then you hang a pot at the focus. And it works best actually if you paint the pot black, because the black pot will absorb more light. The silver pot has different characteristics. It works really well if it's very sunny out, but the black one works better if it's cold out. So it just depends. But all these solar cookers have this very similar idea, where you're focusing the light all at this pot, and then you can cook something in the pot. It only takes about an hour and a half to cook a really nice meal in this thing. It gets really, really hot. They've since come up with a lot of different versions of this. Some that are very commercialized, and these came to be after his patent expired. So he had the right to it for, I think patents go 12 years, and then he didn't renew the patent. He just released it at that point, and everybody has kind of jumped on board afterwards. So there's lots of different versions of this now. These solar cookers, different shapes, different sizes, different, whatever. But originally the idea was to help people to cook in third world countries where there's a real surfeit of wood. So there's just not much wood around because they've been burning wood so much. And this is the case. This is very much the case in places like Africa, Pakistan, a lot of places in the Middle East actually, where there's just not a lot of wood in general, and a lot of people are still burning wood for heat and for cooking and other things like that. And so those things were distributed. There was a huge project in the 80s and the 90s where he and several other people, engineering and science teams and groups, were making these things and shipping them all over the world and distributing them wherever they could. And they're really quite quite useful little things here. Lots of versions. Here they're making a pizza. Actually looks pretty good.
Is it enough to boil water?
Oh yeah,
Like if you,
oh yeah.
so that's a certain type.
This one's kind of like it's kind of cool. That one looks like it's kind of like a rotisserie or something. It's kind of unique one. But in every case, the idea is to focus as much energy into a single place or along a single line in the case of these kind of cylindrical ones as possible, and turn that light into heat. Right? Here's actually one of the ones that was shipped by one of the groups overseas. So you can see that they're being used all over the world now, and it's a really great thing. It's a fun project. We could do it as a project, maybe during finals week. We're not going to be able to do it this week, probably. All the rain and snow we're supposed to get. But, yeah, you can even you can cook bread. That gives you an idea of how warm it can get. Bread usually has to cook at 400 degrees, so it definitely is enough to boil water. Water boils at about 212 Fahrenheit, right? So it takes about the same amount of heat transfer to do that. But this one actually looks the most like the one that he developed. But his was not very spherical because they were trying to make it easy to transport and very cheap so that people could make them on their own if they needed to. So the first ones he made were just cardboard covered in tinfoil, and that's really enough. It doesn't take much more than that.
Couldn't you also get I guess this wouldn't be as cost efficient, but a big lens and just like
Yes, you could do it with lenses, but again, with lenses, remember the light has to go through the material, which means some of that light heats up the material of the lens. So you lose energy that way. And while the mirrors get heated up also, it's not nearly as much. But yes, you could do it with lenses as well. It's much easier and much cheaper to make, a mirror, of course. So, yeah. Lots of these now. They're all over the place. Maybe we should cook a meal using. I've never done that with the class. Last time I did it, I was actually at BYU. It was a physics club meeting. We cooked our dinner in solar ovens.
We could find a really nice sunny day and cook something outside.
Yeah. Maybe we make it a fundraiser for the STEM club. Cook something fun.
Cook something inside.
Let people roast marshmallows around the mirror. All right. So anyway, here they talk about something that I mentioned before, which is this is called it's another kind of aberration. They call it, I can't remember. So this is spherical aberration, where you get light coming into a lens, but at the edges of the lens it focuses more tightly than in the middle of the lens, so that you get multiple focuses, and that's what you get when your eyes are open too big or whatever. So that's what we call spherical aberration. You can also have aberrations from light not coming in parallel. If light is not coming in parallel to your lens, you get different focuses, and that causes blurring effects. But this is what we call chromatic aberration, where we've already learned that light coming into a material splits often because it has different focal lengths for different wavelengths, right? And that's this is what happens, is that your red wavelengths tend to focus further away from the lens, and your blue wavelengths tend to focus closer to the lens. So you get a spreading of your focus again. And you get a rainbow effect. You kind of get a little rainbow edges on your, and this is called chromatic aberration. So one way to fix that is to put in multiple lenses. Put in a defocusing lens that will realign the red and the blue and everything in between to a single point. And these are called compound lenses. And sometimes it's 2, sometimes it's 7 lenses that are required to get rid of all the aberration. But that is another type of problem that you get with lensing effects. So anyway, that covers that chapter, whatever chapter that is, 26, something like that. 22, 26. And then now I'm going to turn you loose to do some more experiments. So do some more experiments, try to get some done today. Tomorrow I will not be in class, but you will go ahead and do experiments. You can come in here and do experiments without me. I'm going to be in McCook tomorrow, unless the weather gets bad, like we have a tornado or something. But it's possible that a winter storm might prevent me from going to McCook. If it's going to be snowing or really high wind, I won't be going, so I'll just be here. But you should come in anyway and try to get as much done on those labs as you can, so that on Thursday we can definitely be doing the eyeball tank lab. I'd like to be here for that because usually people have quite a few questions about that. And in McCook, you do have the eyeball tank. It is in the laboratory there. I can't remember exactly where, but Micah should have. I gave him a map where everything is. And I will send you the lab for that. The eyeball tank, I think, is one of the more popular labs for this class, just because it is so relevant to so many different things. Everybody has an eyeball, for example. But it's just really interesting to learn how the eye works. And you won't even get this kind of detail on how the eyeball works taking a physiology class, because they don't use these tanks. I don't know why. I keep telling them they should, because it's really cool. You get to create an eyeball with, a perfect eyeball, and then you get to create one that has myopia or hyperopia, and then you get to correct it. You get to give it a prescription and see it. You can actually watch as it focuses on the retina. It's a really cool lab. I've enjoyed it since I did it 20 some odd years ago. So anyway, that'll be what we try to get finished this week. Try to get as much as you can done today and tomorrow in these labs, and then we'll move on to the eyeball lab. And then, of course, we'll meet Thursday, and then next week, of course, is spring break, right? So we will not meet next week. Do we have an exam or anything this week?
The week
After spring break?
Yeah.
Well, that's just
Or maybe
perfect.
2 weeks after.
Yeah, because we still have a couple of things we still have to do.
27.
Yeah, 27 has to be done. So, all right. Well, we'll see you later. If you have any questions, make sure you ask. Yes, end my recording.